Okay, this is the second video about electric fields, and we're not going to look at how we calculate electric fields from source charges yet. We're going to talk about electric field lines, which you've seen last year, and this will mostly be review. Now remember, the electric field is something that exists at every point in space, and if we put a test charge at a location, the force on that test charge will equal the charge times the field. If the charge is positive, the force points in the same direction as the field. If the charge is negative, the force points in the opposite direction from the field. An electric field line is a way of representing the electric field in a region of space. So it might look like that. You have electric field lines. They're usually curves, sometimes straight lines, that have a particular direction. They start on positive charges and they end on negative charges. They can also go off to infinity, but they can't end in the middle of your paper unless there's a charge there. They can also start at infinity. Start or end on charges or at infinity, but never in the middle of your paper if there isn't a charge there. Now let's say you want to know what the direction of the field is at a particular point in space. Well, it turns out that the direction of the field at that point is tangent to the field line. And the magnitude is given by the density of the lines, how close they are together. So you have a strong field in this region, and you have a weaker field out here where the lines are farther apart. And the other thing about electric field lines, they never ever cross. To see why, let's assume that they do cross. So let's say in a particular region of space you have an electric field that looks like that. And then we'll put a charged particle here, and we'll say, well, what is the direction of the force on that particle? Is it in this direction? Is it in this direction? Who knows? Well, it turns out you can't have an electric field that has two different values at a point in space. And so the fact that the field lines can't ever cross is a consequence of the fact that each point in space only has one value of the electric field. So, can't have field lines cross. If you're asked to draw field lines and they cross, you did it wrong. Now, the patterns for certain charge distributions, if you have a point charge, the field produced by it will go, if it's positive at least, point radially away in all directions. If it's a negative charge, the arrows will be reversed, but that's what it'll look like. If you have a conducting sphere with positive charges on it, remember all those charges reside at the surface of the sphere, so the field lines will start at the edge of the sphere and point outwards. And it looks just like the fields of a point charge, except that inside the sphere there is no field at all. If you have a line of charge, so charge spread out in a line like this, the field lines will point radially outward from it, like that. You can think of it as a long string of point charges, but that's what the field lines look like. If you have two charged plates, which is very common in circuits, it's called a capacitor, where we have plus Q on one plate, minus Q on the other plate, the field lines near the centers of the plates are evenly spaced and point from the positive to the negative. But then when you get out toward the edges of the plates, the field lines bow outward a little bit. That's called edge effects. It's tremendously hard to calculate, and so we'll largely ignore them. And when we look at two charged plates, we're mainly going to look at the electric field between them, in the middle. And then the other kind of field line that you'll see a lot is a dipole, which means a positive point charge and an equal negative point charge a small distance away. And you don't actually need to calculate the fields. Your book has a section on that, but it's not part of the AP curriculum. You should, though, be familiar with the way they look. The field lines will point from positive to negative, and it'll look something like that. Now, one of your problems is a charged disk. You need to draw the field lines of that. It's a very interesting one. Not one of the ones I'm checking tomorrow because it's a bit of a challenge, but please do make sure that you do it. Last year people didn't because they don't like drawing. But tomorrow I'm going to check question 1. I'm also going to check problems 1 and 3 in chapter 23.